Hello everyone and welcome to Texas Tech University's Project Lab 1 tutorial videos. I am one of the tutors for this course. My name is Daniel, and in this video I'm going to be showing you how to use the IPS sensor or the inductive proximity sensor or the capacitive proximity sensor and input that signal onto your BASYS3 board. So those sensors are the ones right here on the front, the orange and silver ones. And as usual, the first place you should go whenever you are working with a new piece of hardware or a new device that you have never worked with before, you look up the data sheet. So the sensor that's available in the stock room that I grabbed is the LJC18A3-H-Z, and then there's AX, a BX, a CX, TX, and a bunch of other variations of it. So opening up this data sheet, we will see that there are a bunch of different variations, and for having so many variations, they only have one page of data sheet. So as you see, the data sheet does not have a lot of information. So the one we have is LJCA3, this very top one here. And pretty much what the data sheet says is that this device is an NPN DC NPN transistor that works in normally open configuration, and that it has a detection range of around 10 millimeters, and let's see, it has a little bit more information, but the place you want to go to get your information on this device itself is on the label that it has around the top of it. So looking at the sensor, you see that it has a label. I know the camera doesn't zoom very well, but here this silver and blue label. Looking at the label itself, you see that it also says that it's an NPN transistor. It tells you that the wires, the three non-standard color wires, that the brown one is a positive wire, the black one is a signal wire, and the blue one is your ground wire. So it also says on that label that the range is 1 to 10 millimeters, like the data sheet says, and that the voltage to operate this device, the voltage supply ranges from 6 to 36. So you can use any voltage from 6 to 36 volts to power this device. It does run at approximately 300 milliamps, again off the label. And again, like anytime you have a brand new piece of equipment, the first thing is to know how it works. We visited a data sheet. We saw the data sheet does not have as much information as most other data sheet, but the label here gives us enough information to get started. So grabbing a battery from the stock room, I grabbed this 9.6 volt rechargeable battery. From experience, I know that this battery fully charged, so right now I just pulled it off the charger, plug it into my multimeter here, and I do know that this battery does go up to like 11 volts. So even though it says it's a 9.6 volt rechargeable battery, from experience I have seen it go up to 11.5, and when it drains it goes down to like a 7.5. So keep that in mind, because this is not set voltage for this battery. It does range from 7 to 11. So 11 is still a safe voltage to take into our sensor here. So let's go ahead and, using our breadboard here, I will plug the positive to a row and the negative to a row. And now grabbing the pins off of the sensor here. So again, these wires, I stripped them and then I added a crimper pin that's available in the stock room just to make it easy to plug in. So based on the configuration that we read off the label, the brown one is positive, so the brown one goes into my positive here. The blue one is our negative, so blue goes to our negative here. And looking at our sensor here, we see that there's a little red LED or a little LED in the back. And if we put a metallic object, the LED will turn on, showing you that the sensor is working properly. So that's the first thing you want to do, make sure that the sensor is working properly. The next thing you want to do is, now that you see it is working properly, check the voltage on the output leg, so on the signal. So eventually this signal is going to go into our BASYS board to tell you to stop or go right or do whatever you need to do on the rover. But for now we have to see what the voltage is, so that way we can step it down to appropriate voltage that is safe for the BASYS board. So hooking up this signal leg to our multimeter and giving it a common ground there. Alright, so there's a common ground, and we see that the signal leg of the sensor, when it is not detecting anything, is at 9.28 volts. So on a source that we saw that was 11.5 volts, the output, the signal output coming out of the sensor is at a 9.28. So then that automatically should throw up a red flag, because now this 9.8 volts the signal cannot go into our BASYS board. If you are familiar with the data sheets, which you guys should have all looked over the data sheet for the BASYS board, you do not want to input a voltage higher than 3.3 volts to the board, or you could damage the PMOD port, which are going to be the inputs to the BASYS board here. So now that we know how our sensor works, now we have tested it, hooked it up to our multimeter. You could have also done this with the oscilloscope that you have. But now we have identified an issue which we're going to have to address. So this output voltage of 9.3, we're going to have to find a way to step down to a safe voltage to input into the BASYS board. So I'm going to unplug everything real quick. And a few different options that I've seen been used for this issue here, for this common problem. The first one that I wanted to bring up is going to be, let's go back to our screen here, and the first one I wanted to mention was the optocoupler. Optocoupler is an IC chip, so it is a little silicon chip that looks like this. If you go here to the Wikipedia page, you see that it's just a chip, a four-legged chip. So on two sides, this left side is the input, 1 and 2 would be the input, and 3 and 4 would be the output of this chip. And as you see, it is completely separated. And the way it works is, as current flows on the left side, we call this the high side. So as current flows on your high side, which refers to your high voltage, it sends some photons over, and then this photo transistor allows current to flow on the low side. So for our case, this would be your 9.5 volts that is coming out of the signal leg on our sensor. And as the current flows, the current would allow it to flow on this side. And on this side, you can have, say, 3.3 that can go into the BASYS board. But that is the first option I want to mention. Optocoupler is available in the stock room. They have the single chip, which is looks like this is just one optocoupler on a chip, and then they have the quad optocouplers, which is four of those on a longer chip. Another thing I wanted to mention that you could use would be a relay. A relay works a little bit similar to the optocoupler in that you have two isolated sides. So let's go down to a schematic. Alright, so here in this most basic schematic, single pull, single throw relay here, you see that on the left hand side you just have an electromagnet. So as current flows on the left hand side, the high side, it would charge this electromagnet and cause the electromagnetic field to close this switch on the right side, allowing current to flow on the right side, which would be your low side or your 3.3 volt side. So a relay would also be an appropriate option. You have again your high side and your low side are safely separated and isolated to protect your BASYS board. One thing to keep in mind with the relay is that there are many different modes, many different types, and you got to make sure you are using it in the correct mode. Alright, so the third option I wanted to mention would be a voltage divider. So you guys should be familiar with the voltage divider. It's pretty simple, so using resistors or inductors in the future. In this case we're going to be using just resistors, but using resistors you have a known Vin, and using a ratio of resistors you can get a known Vout. However, it is important to remember that your Vout is dependent on your Vin. So in our case, we are using the Vin of the 9.6 rechargeable, which we know ranges from 11.5 to 7.5. So if the Vin changes from 11.5 to 7.5 as it drains power, then the Vout is also going to change voltage. So what you thought you had was 3.3, as the battery drains, it changes the value of it. So if you want to use a voltage divider, which you can, you would want to do some sort of voltage regulator to regulate a set voltage that will not change as the battery drains. So I actually decided to go with the voltage divider. Here on my breadboard, I utilized the 8-volt regulator, the L7808 8-volt regulator that I used in Lab 3. These are available in the stock room also. And the 7808 is similar to the 7805 voltage regulator. So there are many different voltage regulators, 3.3, 5 volts, 8 volts, and plenty others. So a regulator that would work with our 6 to 36 volts source that we need to power up the sensor would be this 8-volt regulator. The package we have here is a TO92, so we see that on the flat side, pin 1 is Vout, pin 2 is ground, and pin 3 is Vin. And here this test circuit tells you that you do want a 0.33 microfarad cap on the Vin to ground leg, so 3 to 2 needs a 0.33, and your Vout to ground also needs a 0.1 microfarad, so 1 to 2 needs a 0.1. So make sure you set those capacitors. What they do is actually keep the change from affecting your output. So what we want is this output to be a regulated 8 volts regardless of what the input is. So the capacitors allow it to remain a steady 8 volts even though that the supply is changing from 11 down to whatever it changes. So that's your set output. In the future for Lab 3, you will also see that these capacitors remove a lot of noise that can affect your signal. So again, just get these capacitors and set those up. If you keep looking through the data sheet, you'll see there's a lot of more information on how to use the device. Here on the electrical characteristics, make sure you are looking at the 7808. So here at the top gives you the version of it. So here is the 7808. This is the one that corresponds to the 8-volt regulator that I'm using. So going back to our camera, I show you my 8-volt regulator here. So on the top of this breadboard, on the right hand side we have our 8-volt regulator, the 7808, with the two capacitors in the back, one going from pin 1 to 2 and the other one going from pin 3 to 2. So these two wires in the middle here are our input voltage. So our input voltage go to the appropriate legs, and then our output voltage go to this right rail. So I'm using this right rail as my 8-volt rail, and here on the left hand side I have a 3.3 volt regulator that uses the same input voltage, but then the output voltage goes to my left hand side. So my left hand side is my safe 3.3, my right hand side is my 8 volts, and I'm going to plug in the 9.6 rechargeable in here. So if I do that, first thing I do is check my rails to verify that our appropriate voltages are there. So grabbing a jumper real quick, we can plug it into our 8-volt rail and see that it displays a 7.98, so that's 7.92. So that's our 8-volt rail, which is good to go. And our 3.3 volt rail, which is showing a 3.2627. So, alright, both of our rails are good to go. The next thing we would like to do is, now that we have our 8 volts regulated, and again it's on the right hand side of this rail, I can go ahead and plug in our power legs from this sensor. So again, brown is positive, blue is negative, and we power those ends. We want to give a quick check to the sensor. I'm going to go ahead and plug in the sensor to the multimeter. So now that we see the multimeter showing a 5.84. That 5.84 is coming off the signal leg of the sensor. So when the sensor is not detecting anything, it sees a 5.84, it puts out a 5.84, and when it does, you see the LED turn on in the back and it drops down to a 0 volt. So 0 when it detects something, 5.84 when it does not detect anything. And again, that's being powered by the 8-volt regulated source, so as this battery dies, the output would not change. Alright, so this pulled out a leg real quick. Let me plug this back in. Alright, so now that we have our output, our regulator set up, we know what the voltage is on our output. The next thing you would want to do is set up your voltage divider. So a quick voltage division review here. We see that all we need is R1 and R2 to set up this voltage division. We know we have our VN, which is a 5.84, and we know we want a Vout of 3.3 volts. And again, Vout does get measured across R2. R2 does get grounded on one side, and the other side connects to R1. So, knowing that we want a 3.3 volts on our Vout, and we have an input of 5.84, we can do a quick division there and see that our ratio of resistors R2 over the sum needs to be of 0.565. Alright, so 0.565 can also be written as 56.5 over 100, which equals to our ratio of R2 over the sum of the resistors. And if we cross multiply here, we get that R1 plus R2 equals 100 R2 over 56.5. And now picking a large R2, you want to pick a large R2 so that we have the correct biasing that we need for this NPN transistor. So picking a large R2, we plug it in and see that R1 needs to be 470 kilo ohms. So now that we know our R1 and R2, R1 470 kilo ohms, R2 360 kilo ohms, I can go ahead and set it up right here on my breadboard. So here is my R1 and my R2 has appropriate values that we just came up with on our math there, on our voltage division math. So I can grab the signal leg that we know was a 5.84 volts, again 5.84. We can plug it into the input of this voltage divider network. So plugging it in there. And now we can check on the node of these two resistors. So right where the two resistors are meeting, we can see the output of those resistors. So now looking at the voltage across R2, we see that we get the 3.3 volts that we wanted. And if we check the sensor now, so the sensor is over here, and if I grab a metallic object and put it in front, you see that our voltage drops down to 0 volts. So 0 volts when metallic objects is present, 3 volts when nothing is present. And now we have a successful voltage divider network that we can input into our BASYS board. So now that we have all of our wires and signals at the correct voltages to take into our BASYS board, now we can go ahead and program our BASYS board to take in this IPS signal and turn on an LED. So go into my desktop, opening up Vivado here. And I'm going to create a new project. Hit next. I'm going to call this IPS underscore tutorial. Hit next. And it's RTO project. Do not specify sources at this time. Next. And here we family Arctic 7, package CPG 236, speed grade -1, and then this XC7835. Hit next and finish. And that should create a empty project for us. So now that we have our empty project, we can go ahead and click up here in sources, hit add source. We want to create a design source, so hit next. We want to create a file, make sure it's a very long type, and I'm going to call it IPS underscore tutorial. Hit OK. And highlight it, select finish. Inputs, so let's go ahead and put our input. We're going to have an input called signal. It's an input, and then we're going to have an output called LED. So output, and then LED. Hit OK. And that should have created the module for you. You can double click on it here in your sources to open it up, and you should see that it's a blank module with the standard headers, standard time scale, and all we have is our input and our output that we desired here, that we chose. So a quick module to test this would be that you would want to assign your output, which is LED, to be equal to not your input signal. So the tilde is just an inverter. So as we know, our sensor gives you a 0 when it detects something and a 1, logical 1. So 3.3 volts is considered a logical 1 for the BASYS3 board. So the sensor itself puts out a 0 when it detects something and a 1, logical 1, when it does not detect something. So therefore I'm inverting it, so it turns on the LED when we get the 0 and it turns it off when we have the 1. Alright, so that module is done. We can save it, go check for syntax, and now we can come over here and run synthesis. So that shouldn't take too much time. Alright, so that's good to go. We can close this out real quick. Before we move on, we want to make sure we go up here to Tools and go to Project Settings, Bitstream. Make sure you have selected bin file here. So hit Apply and then OK. So the bin file is going to be the file that we program onto the memory of the BASYS3 board. So that's why we wanted to select that. Once you have done that, then we can go ahead and run synthesis again. Okay. So in order to program onto the memory of the BASYS3 board, you want to make sure, alright, so this is BASYS2. Let's look at an image of the BASYS3. So this jumper on right here next to the USB, this blue jumper needs to be on the top setting for us to program onto the memory. So the top setting, the top two pins would put you on QSPI mode, the middle 2 pins will put you on JTAG mode, and the bottom 2 pins will put you on USB. So make sure that is set to QSPI, so the top 2 pins. And now that the synthesis is finished, go ahead and open Synthesize Design, hit OK. This will open up the design real quick. And here in design, we are going to go to Tools and Edit Device Properties. So that one. And under the General tab, we want to enable the bitstream compression. So hit that one True. Go to Configuration. You want configuration rate of 33 megahertz. So this is configuration of the JTAG port. So that is at 33 megahertz. And now configuration mode, you want to go down here to master SPI ×4. So check that box And now you can hit OK. Now you've done that, you can go ahead and close this synthesize design. Make sure you save it. So hit OK and hit yes on the save. Hit OK. We haven't created an XTC yet, so here it's making us create one. So we're going to call this one, I'm going to call it IPS underscore tutorial underscore XTC. So for those of you who have created XTC, it is a design constraint file which maps out your inputs and your outputs to their physical locations on the BASYS3 board. So once you've done that, you can go ahead and close it again, hit OK. That should have closed it, brought you back to this. Now you can open up your constraint file. So checking on constraint, you see that it labeled it exactly what we named it. So double click on that. You see that the only thing on this constraint file right now is the settings that we just checked or selected under synthesize design. So to create your XTC file, you want to go back to our Google and Google BASYS3 Master XTC. So the Digital Insight again does have it. The one that I like to use is this resources GitHub one. It has it right here. So I'm going to alright, so in this project we don't really need everything. So if you scroll through this, you see there's almost 300 lines of every component available on the BASYS3. Tells you the location, name, and everything you need to use that port or that component. So for us, we just need, let's see, our module just has one input and one output. So looking at our BASYS board, we know that our input is going to go into one of these PMOD ports, right? So one of these 4 PMOD ports is going to have our input, and our output is going to be displayed on one of these LED. So coming back to the master XTC, we can select a PMOD port. So if you see, they're all labeled, so JA, JA1, JA2, JA3. So let's select JA1. So just highlight everything that says JA1 here. So line 126 and 127. Control C. And we're going to paste it in our XTC at the bottom. Control V. And we're going to remove these pound signs. Those are the comments symbols for the XTC. And now everywhere we see JA0, we're going to replace it with our signal name, or input name. Our input name is signal. So therefore, we will replace the JA0 with the word signal. And same right here. Signal. And now we can move on to our output, LED. So LED is all uppercase, so we'll have to replace the name with the uppercase LED. So going back to our master XTC, scroll up to LEDs, here we go. So I'll use LED 0, which is one on the farthest right. And Control C, paste it in my master XTC here. And remove pound signs. And change the name. And now we can go ahead and save our XTC. And rerun our implementation. So implementation, run that. So now we are running implementation to map out all of our inputs and outputs, and after implementation, all we have to do is generate the bit file to program our device.